Welcome to the next in a series of lessons on limits. This is lesson number 4. All right, so today we're going to look at evaluating limits and thinking about continuity. So if you think about continuity, for instance, let me grab a wire. This wire represents a function. I can slide my fingers from one end of the wire to the other, and I would never have to take my finger off the wire to get to the one end. That's continuity, and it doesn't matter what the shape is. If it's got continuity, right, it will always be able to draw that with one smooth, continuous line with my pencil on the paper without ever having to lift it up and move it. That's an easy way to understand the definition of continuity. So let's take a look at a function, the limit of e to the x. First of all, we had to know what e looks like. Is it a continuous function? And it is a continuous function as you look at it across the domain of all real numbers. It has a range limitation, more than a domain limitation, but we'll look at this. So basically, this is some number to the x, which means the variable is not in the main line, but in the exponent, which makes it an exponential function. And we know an exponential function looks like this. Kind of starts at an asymptote level. In general, it'll cross 0, 1, and then go up at an ever-increasing rate. Exponential growth of debt or wealth, right? Exponential growth of population. That exponential shape is always the same. Why does it generally cross through 0, 1 when most functions' parent location is 0, 0? Because when I put in a 0, any number that's not 0 raised to the 0 power is 1, so that 0, 0 home point is in exponential functions is 0, 1. Okay? So e to the 1 I can assess by putting in a 1 and hitting the e to the x button on my calculator, or typing it in the syntax version. So go ahead and do that, and I think you'll find it's 2.7 something, or something like that. I don't have my calculator handy, and frankly, you know, I don't memorize everything, because I can get it, okay? But when I put in e to the 1, we can say safely that e to the 1 is e, and you can know that numerical value by putting a e to the 1 in your calculator to get it. So what we're looking at here is, in this case, e to the 1 is e, and we want to say to ourselves, okay, does that function have continuity? And it does, all right? Because that function looks kind of like this. And it never touches this axis, because I can't start out with nothing and raise it to a power and make it become something. 0 to the 10th, 0 to the millionth, 0 to the billionth, 0 to anything except 0 is 0. So if I started at 0, I couldn't do it. So what happens is my asymptote is actually here at y equals 0. Okay? And I approach it, but I never get to it. So in other words, I can grow exponentially, or I can decline back down that line, so to speak, but I'll never get to nothing. What happens in reality is I grow exponentially, and then my resources for growth are diminished in such a way that I drop off to extinction, you know, if I'm a population, right? So, or I make that S curve in reality, but if I extend it and artificially push it, I could literally drop to 0. At that point, I don't keep going. I don't have less than 0 members of a population. I have none. No breeding partners means extinction. So that's kind of a way to think about why this is at 0, 1 and not 0, 0. I can't raise 0 to a power and make it more than 0. So if a function, and that's what I see when I see f of x, if a function is a line that I can draw without ever lifting my pencil, did I draw that without lifting my pencil? Yes, I did. If I can draw it without ever lifting my pencil to move to another place to finish the line, then my function is continuous. That's pretty much straightforward stuff. Continuous or not? Yes. Okay, continuous. I can pick any point A and find f of a, so could I find the limit anywhere on that line? Absolutely. And as I approach it from this way, the outputs will squeeze, the box, epsilon delta is all in place, right? So there is A input, f of A output, because this is f of x. Get used to this notation. That's the mathematical notation for input, output. Input, output. Output at that input value. I don't want A f of B, A f of x. I want A and the output at A. If I try B, I want the output at B. This is saying x is my input variable. A is a discrete numerical value I put in. So be careful. When you see those things, A's and B's and C's, they're talking about this is a number. Whereas X is, this is any number. A is a specific number. They just don't call it out. Okay? Continuous or no? I'm going to tell you the answer depends. How'd you like that? The answer depends on what interval I'm evaluating it at. Am I evaluating it for all real numbers of my domain? If I'm doing that for all real numbers, is this continuous? No. Here I go. There's a hole. Ah! I did not fall through the hole. I had to lift up and jump over it and finish. But now I'm here, and this doesn't connect. But if I, go up here, then now I'm back. I'm going, over the hole, put a dot back down. That's clearly, I had to lift my pencil up and down to draw that. Clearly not continuous. But if I said, is it continuous from negative infinity to A, not including A, as far as I can tell is yes. But as soon as I go past A, the answer is no. Between A and B, not including either one, yes. But if I go past B, no. So you see, you've got to be careful. You can't just say, no, not continuous. You've got to know which part of the graph they're asking you about. When you analyze that interval, you can say continuous or not. That's very, very important. Continuous? Without more information, I can say I don't know. I could ask a clarifying question. Over all real numbers? If the answer is yes, then the answer is no, because when I get here, I've got to jump. But if is it continuous between negative 1.1 and negative 1.9? Yes. You see what I'm saying? So be careful. This is the nearest integer value. And what this is if I put in an input and it is above slightly an integer, I round down, or below slightly an integer, I round up, depending on whether this is the next nearest large or next nearest smallest integer. And the notations can vary. I believe this is the next nearest large integer, so that's the way it goes. Oops, don't want that. Want that. Greatest integer function. That's what that's called. Okay? This has jump discontinuity. See, the other one I had multiples, right? So that's screen 11. Let's go back to 8. Is there a jump discontinuity in 8? Is this a jump discontinuity? No. But this, boom, yes. Is this a jump discontinuity? Yeah, because I jumped up, made a dot jump down. But this, there was no other dot, was there? So that's not a jump. That's a jump. That's a jump. Okay? Important. So here's another set. Okay? This is an asymptote. So if you look at this, I really probably should have done this to show that those things were going on and on continuously, or let's say forever. Continuously might not be a good choice of words in this case. Continuity depends. Over all real numbers? No. Can you define over all real numbers the kind of discontinuities you see? Right? Well, this one is a hole, right? But at this hole I jump, so there's a jump discontinuity there. This is not a jump discontinuity. This is a hole, and this is an asymptote discontinuity. Okay? Name the discontinuities. Okay? At x equals 2, I'm jumping. I get to 2, I jump up, and I finish. At x equals 4, it's an infinite discontinuity. Why is it called infinite when there's an asymptote there? We're going to look at that in just a second. And here, where there's a hole, it's only discontinuous at that one single point. So it's called a point discontinuity. So let's look at why this is called an infinite discontinuity. All right? Why is that called an infinite discontinuity? We're going to list those intervals in a second. But before we do, let's talk about what happens here is when I put an input in, I get an output that's unplottable, which we kind of call that undefined. Okay? Let's stick with undefined instead of indeterminate. Well, what this is asking me, if you think about it, if I looked at that, if I said how many times can 1 go into 2, my answer would be 2, right? Check. How many times can nothing go into 1? That's a whole different kind of question. Whole different kind of question, right? So that question is, let's imagine like the old question was, how many times would 1 go into 2? If I had a cup that held 2 and I put 1 into it, it would be half full. If I put another 1 into it, it would be completely full, and that's why we could say that 1 goes into it twice. But let me take this cup that holds 1, and I'm going to reach in my pocket, because that's where I have nothing oftentimes, and I'm going to put nothing into it. Is it full? Is it partially full? Let me put another nothing in. How many nothings can I put into that cup that holds 1 whole value before it becomes full? Will it ever be full of nothing? In reality, the answer is no. So I could do that inputting nothing forever, and when something goes on and on forever, we can say that it's gone on infinitely. That means 0 will go into 1 as many times as you want to do it, and it'll never be done. And that's what they mean by infinite discontinuity. Okay? That's why they call it an infinite discontinuity. All right. So what are the intervals of continuity? Well, I'm assuming that to the left of this arrow and to the right of that arrow is all continuous, because that's all I can assume. I can't assume a discontinuity. I really can't assume continuity, but we're going to assume a continuity because we were told to name the intervals. So this direction here is going on forever and ever to the negative. This direction is going on forever and ever to the positive. So I'm going to have a negative infinity until I run into my first discontinuity, which lives where? At 2, right? When I get to 2, I got to jump discontinuity. It would have been a point if it had continued, but it jumped. Now this can't be solid and solid, because for every input there is 1 and only 1 output. And we're working with one-to-one functions here. Okay? So if I had a solid dot, that would be 2 outputs. This wouldn't be a function. So this is a one-to-one function because there's 1 output for 2, and that's an empty space. So I don't include 2 here, do I? So it's a... But on this part, do I include 2? I absolutely do. So can I just use a comma there? I don't think so. I don't think so. I have to include 2 somehow. Ah, that's how. The square. Remember the square bracket I said was inclusive? This is exclusive. This is inclusive. How come I don't include 4? Do I ever get to 4? No, if you remember, I go down and down and down, getting closer and closer to 4 forever, because this is an infinite discontinuity. So then I'm going to have to hop over 4, but not from way to infinitely low, up to infinitely high, and then continue on down, because I'm going left to right as I analyze. So I'm going to go from 4, here, let's go ahead and put that. I don't like those. What should be where those commas go? We're going to fix that in a second. Okay? But right now we're making a list. So I'm going from 4, not including it. So you see here 2's in something, but is 4 in any of this? No. Okay? Over to 6 where there's a hole. Since there's a hole in 6, is 6 included in the hole? And isn't the hole existing wherever 6 is? So the next interval is going to go from 6, again, not inclusive, to infinity. Now I'm going to ask myself, what is wrong with this notation I've got right here? I'll tell you what's wrong. This should have unions, because that interval is this piece with this interval and that interval and that interval. When I do that, that is my domain. So the reason they didn't put the U's in is because it said to do what? Name and label the discontinuities, yes. List the intervals of continuity. So if I left the U's out, it really was a list, wasn't it? All right? But I'm putting the U's in there because this list, you might as well just put the U's in and call it the domain. Because if you write the domain, you've listed the intervals of continuity. Okay? because it's continuous over this domain. It's continuous over this domain. It's continuous over these x inputs, which is domain. That x input doesn't work, but here it does. Continuous, discontinuous. How many discontinuities are there? 1, 2, 3. 1, 2, 3. Simple as that. Okay? Continuous or not? Your question should be over what interval, Dr. Taylor? Over the interval of -1 to 1. Yes. Over the interval of all real numbers? Doesn't seem to be. Looks like half a circle, doesn't it? Well, look, what could I not have under a square root sign and still be in the real numbers? Can't have a negative number, right? So that means as long as I am between 0 and 1, I'll be cool here. Can I take the square root of 0? Yes, 0 times itself is 0. But if I were to go beyond that, I would not. So in this interval, it is correct. It is continuous. Okay? Over all real numbers, is it continuous? Well, let's see. No. How come? Why did I say no when I said let's see? Now I know that I'm getting dark here, but I've got the light so that we'll see the board. My face is ugly anyway. So, what about 2? First of all, is there even a line drawn for over the outputs of 2? No. Why not? What is 1 minus 4? -3. The square root of -3 is imaginary. So it's imaginary when I get to that point. And I don't want an imaginary value. I want a real value for continuity. So it's not continuous over all real numbers, but it is continuous over -1 to +1, inclusive square brackets. Okay? Over 1 to 2? No. Right? Over -1 to 0? Yes. Right? Counting -1, but I don't have to because it didn't say inclusive, did it? But I could have. To 0? Is that a solid line without any breaks? Yes. So you can see visually inspecting it is it's just as good, right? It's even better. I don't want to put a bunch of numbers between 0 and 1 and hope that they work, and I didn't skip one that didn't work by accident. But when I can see the shape, I can look at it. Of course it's continuous. I can see it's continuous. So it's very, very important. Just continuity, not that tough. Okay? What if f of x's domain, what is f of x's domain of continuity? Well, we talked about that. What is it? From -1 to +1. Yes, and I could put it that way and that way. Why? Because I tested it. What I really should see here is a solid dot, right? That's what I really should see. It would be better, so let me make another slide. It would be better to say that works, but I tested it by plugging it in. -1 squared is 1, 1 minus 1 is 0, 1 minus 0 is 1, so that works. +1 squared is 1, 1 minus 1 is 0, square root of 0 is 0, 1 minus 0 is 1, so that worked. So that's why I was able to use square brackets. I used the square brackets because the blue dots existed. They were defined when I put them into the function. Okay? So, here's a function. F of x equals x plus 2x cubed all to the 4th power. Okay? And in here it's got a domain a equals -1. Right? So here's a g of x, right? And g of x is x plus 2x cubed. And here is f of x, which is this thing to the 4th. Well, look at that. What am I trying to point out here? It goes back to Algebra 2. What am I trying to point out here? I'm saying this could be broken apart. There's this inside function, and there's this outside function. And if I name the inside function g, then I'm taking f of g of x. Composite function. That's what that's about. All right? So I can put in my stuff. I put in my number -1. So if I did g of -1, this is what it would be. right? If I put in f, right? Well, I know what g of negative 1 is now. So f of negative 1 is g of negative 1 to the 4th power. And I get an outcome of 81. F composite g is 81. The reason I went over that is that's an important thing, because when you're doing continuity, you sometimes have to think about that function in its pieces. And sometimes you have to think about it as how the pieces work together. Okay? So, let's take a look at this. When we're looking at these kinds of discontinuities and what happens and how they happen. So I have a polynomial function. It could have as many, this has got 1, 2, 3, 4, 5, 6, 7. Let's call them 8, 9. Let's say those were peaks and valleys. So if that was 9 curves, the function would be to the what power? What degree function would be? If those were 9 curves, it would be a 10th degree function, right? Because the degree minus 1 equals the number of curves from your 4 questions. If you didn't count those as curves, then it would be 8. So that would be the 9th, right? 9 minus 1 is 8, the number of curves. So however you think about it. All right. So this is a function that is continuous. Polynomial functions are continuous. If they've got a rational piece, now I've got a place where it can become undefined. So a rational function can have an asymptote or a hole. This is an asymptote. Okay? I might dive down on both sides. I might dive down and up on the other, both up. But I'm not touching that asymptote. That's where the discontinuity exists. On each side of the asymptote, they're continuous. So if my region of continuity is on one side or the other, I'm good. If it crosses the asymptote, then I have a discontinuity problem. Okay? And imaginary roots, really an issue, okay? And you got to be careful, like when you take, here's a 3rd power, but when I take a 3rd root, you see I have, for every input, I have 2 outputs. So what happens, you end up only looking at 1. This is actually a 3rd, here's a half. 3rd doesn't have 2 outputs, but a half does. So when I'm looking at a square root, I've got to look at one piece of it. Otherwise, it's not really a one-to-one function. And that's why they only consider 1 root. But when I take the square root, I don't know whether it's positive 2 times 2 that makes 4, or negative 2 times negative 2 that makes 4. So I have to consider the plus and minus root. And those roots, that's it. That's considering the positive root. That's considering the negative root. Okay? So that's how discontinuities happen. Okay? So here's one more. I want to ask yourself, is that relationship true? In other words, is this continuous over that interval? So I'd like you to try that. You try that now and prove to me it is. Okay? So here we are. And I know this was on the board. Oops, I forgot to have it erased. What did I do? I said, well, let's test it. I feel like that this is a polynomial, right? It's actually a line, right? Which is a polynomial, 0 power, right? You know, linear. So or to the 1st power, I should say, my bad. I'm looking at that and saying, hey, there's the rational part that could mess with me. So let's figure out where that's undefined. And of course, when I do that, I figure out that x cannot equal 2. So it can't equal 2, but does this say that x equals 2 in that interval? It does not. Equaling 2 would be square brackets, wouldn't it? Can I go on and on to infinity? Absolutely. 3 minus 2, 4 minus 2, 10 minus 2, a billion minus 2. Those are all numbers that count. Only 2 minus 2 would give me an undefined value. So I could have went open parentheses 2 to negative infinity as well, right? But I couldn't include 2. 2 was not inclusive. Okay? So I can go to infinity. Oops. All right? What I can't do is go to 2. All right? Now, what I'm doing here is as I'm talking about an infinite limit, which we're not going to do till the next lesson. So let's ignore that, and I think that means we will ignore that little bit and touch base on it the next lesson, the infinite limits lesson. Limits as x approaches infinity is what I'm saying. I can have x approach something and get an infinity, but an infinite limit is when I'm letting x go to infinity, and see what happens to that value. And there's a really shortcut way I'm going to show you that's going to eliminate a lot of BS. And it's way advanced, so you're supposed to learn it way much later. But if you learn it now and apply it now, it takes care of everything. Okay? So, when I plug in a 0, I got 0, 0, 0, 0, 0, 0. 0 over 0. Can't do that limit. But what do you notice about those terms? Top and bottom. Take a second. Okay, what did you get? Right? I see there's some powers of x. I see there is not a single term that doesn't contain an x. When that's the case, I'm off to step 2. Plug it in, didn't work. Step 2, factor. What am I going to factor? I'm going to factor an x out top and bottom so I can get rid of them. Yes. That's going to give me a chance to not have 0 on the bottom. I don't care what's on top. If 0's on bottom, I do. If it's not, I'm done. I can figure it out. It can be 17, 15. I don't care. As long as there's not a 0 down there. So let's factor that 0 out, top and bottom. Can't do that. Don't forget, we discussed that a few lessons ago. You can't undo addition or subtraction with division. I have to have factors. I have to undo multiplication. So let's go on. When I take an x out of this, it becomes x squared. If I take an x out, divide an x out of that, it becomes x. When I divide an x out of 2x, it becomes 2. When I divide an x out of that, divide an x out of that. When I undistribute, basically, is what I'm doing, leaving me with x over itself. And x over itself is really another fancy way of saying, you got it, 1. And what's 1 times anything? Itself. That's why we can cancel, not because we can make them magically disappear. We cancel because they became a 1. And 1 times blah is blah. So I don't need to say 1 blah. I can just say blah. What do you have there in your lunch bag? What is that red thing? It's an apple. Right? I don't have to say it's 1 apple. What is that? Apple. Even though that's incomplete sense, it's like, oh yeah. Well, if they say, what are those? Then I don't say apple. I say apples. Then there's a quantity I have to quantify. We accept the quantity of 1 because we can visually see that there's a thing there. And that's what's happening here. 1 of those, and that 1 we're mathematically eliminating. Okay? It's not that hard, but you know, there's a reason why we do everything. And most times you say, oh, just do this. And then you remember it because it's easy, but you don't know why. And then you don't have the insight to undo hard problems because you don't know why you're doing half the easy things you know how to do. So you don't know when they apply, so you do the easy thing at the wrong time, then you're wrong and you wonder why. But you don't know because you don't have the background knowledge. It's so important to have the background knowledge. All right, so does this factor? 2 times 1? Yeah, but those have to be the same signs. I can't do that. So that's not going to factor, right? But when I do plug in my zeros, what happens? When I plug in my zeros, booyah, I get a 2 over negative 2. What is 2 over negative 2? You got it. It is negative 1, and I'm done. All right? So this is how you do those. We're going to look at maybe one more, and then we're going to call this lesson done. Bang. I want to look at this because how do you factor a cube? If you think of this as x cubed plus 2 cubed, that's the sum of 2 cubes, because 2 cubed is 2 times 2 times 2, which is 8. So what that means is this is a and this is b in this format. If I'm adding them, it's the binomial as it is without the power. Basically the cube root of that and the cube root of that. This number squared, these two numbers together, and this number squared at the end. And the middle sign is always the opposite of that. So if this was a plus, it's plus minus. If this was a minus, it's minus plus. It's very straightforward. Learn that. Memorize that. That's an essential memorization piece. Okay? So what that means is I can factor that bad boy out. Okay? By saying x cubed, 2 cubed. Right? And I can do that and write that as x and x squared. Right? 2x. And 2 squared, if this is plus, that's got to be minus. The last one's always plus. Now I do factor the bottom. You do it. Okay. And what did you get? Well, I got, x plus 2x minus 2. That wasn't a difference of 2 cubes at all, was it? I tricked you, didn't I? This is x squared plus 0x minus 4. And the only way that I get a 0x is for the two middle terms to combine. So that must be positive 2x and negative 2x. So the difference of two cubes is always the square root of the first, square root of the second. Conjugate pairs, plus and minus. That's what that means. And look, the x plus 2's cancel the giant 1. Now can I cancel the x with the x? No. Right? This is no longer, this product cancels. There's no more products here, are there? Right? So I've got to look at it in its rewritten form. And I plug in my values, negative 2. What's negative 2 minus 2? It's negative 4. I don't care. I'll figure it out, but I know it's going to be right. I know I'm done. I know now I'm at the answer point. I don't have an undefined scenario anymore. And when I do that, I get 4 plus 4 plus 4 over negative 4. Obviously, that is 12 over negative 4, which is negative 3. L equals negative 3. And that's what we'll call it a class.